In the beginning. Well, you already know the story by now. Everything was compressed and condensed into a tiny point smaller than the period at the end of a sentence on a page. It didn't explode out, but more of kind of just started expanding from itself. There wasn't any borders that it expanded out into, so much so as the borders themselves started expanding. What are exactly the borders or edges or outlines of space? Is there an outside of space? These questions are kind of unknown and debated among physicists right now. What was before the Big Bang is another debate. Physics didn't operate back then in a way we can currently comprehend. Was it just a timeless point where everything was compressed and hot? Was it a more primordial, less structured universe with different cosmological constants? Was it previously a universe like ours that experienced heat death before somehow regressing and collapsing back into a small point? We don't know. But we can actually tell a shockingly large amount of stuff from things like the cosmic background radiation, as we are basically able to look back at the earliest light in the universe, as it took so long to reach us that by the time we look at it with our telescopes and microwave telescopes, the photons, billions of years old, kind of act like a cosmic picture, letting us look all the way back to some of the earliest eras of the universe as we know it. The cosmic microwave background radiation, or CMB, was caused by an event known as recombination, or photon decoupling. From early on in the universe's history, but still 380,000 years after the Big Bang. Before that point, the universe was a hot, opaque plasma, with free electrons scattered photons constantly so light couldn't travel in a straight line for very long. Kind of like trying to see through fog. Once the universe cooled enough for electrons to bind to protons and form neutral hydrogen atoms, that fog cleared, and photons are suddenly free to travel in straight lines forever. Those newly freed photons, stretched out by billions of years of cosmic expansion, are what we now detect as the CMB. But let's back up a bit again. To begin, right at the start of the universe, right alongside the Big Bang, were the fundamental forces of nature, which are also known as force-carrying fields. A field is an all-encompassing, invisible, sometimes fluctuating or energetic underlying medium that goes throughout the entire universe. Every section of space contains all the fields, and there are quite a few, 17 distinct ones known of currently. The one we would be most familiar with is the electromagnetic field. Consider how there can be photons just about anywhere. You can shine a flashlight anywhere and cause that area to light up. The medium that can be filled with and contain those photons in the first place, and what those photons are energy fluctuations of in the first place, is the electromagnetic field. This is why every photon is exactly the same as every other photon, and why every electron is the same as every other electron. They are all fluctuations of their respective field. A photon isn't a little ball traveling through the electromagnetic field. It is a fluctuation of the electromagnetic field. An electron is a fluctuation in the electron field. Even regular particles of mass making up everyday common materials are just fluctuations of energy in the mediums of their respective fields, according to modern quantum field theory. There are 6 different quark fields, one for each type of quark, and also a separate gluon field. 8 different ones, actually, but whatever. All layered over top of each other, all filling space simultaneously. Don't get these confused with the Higgs field, though. That is also a field, and its relation to mass is that quarks interact with the Higgs field as they move. That interaction acts like drag or friction, which causes quarks a slight amount of mass. No Higgs interaction means the quarks just glide along at light speed, weightless. Strong Higgs interaction means a lot of drag and you get a heavier quark. It should be noted that this applies for very fundamental particles like quarks and electrons. This is a consensus view on how they acquire mass. But for larger protons and neutrons, they get most of their mass from the strong force, another fundamental force, also a field, mediated by gluons. The binding force holding together the quarks is the strong force, and gluons are the carrying particle representing the strong force, hence quarks are binded by gluon. The tiny amount of mass the quarks get in the first place, though, is caused by quarks interacting with the Higgs field. As said, it slows them down. Anyways, in the earliest moments after the Big Bang, it's believed that in the first fraction of a second, the universe was so hot that what's called the electroweak force hadn't yet split into the electromagnetic field and the weak force, also a field mediated by W and Z bosons. And every fundamental particle, quarks included, was at the time technically massless, just flying around at light speed, no resistance, no weight, kind of like pure energy almost. The Higgs field way back when had no fluctuations throughout itself. It seemed to not yet have turned on, so to speak. So it was there, but it was flat and empty and doing nothing. Then, as the universe cooled past a certain temperature, the Higgs field got activated, so to speak, acquired a non-zero value, meaning it started doing stuff. At around the same time, something called the electroweak symmetry broke. The weak force and the electromagnetic force split. When the universe was really hot, the W bosons and Z bosons and photon were all under the management of one field, the electroweak field, one unified thing, and its excitations were interchangeable. But once the Higgs field turned on, it started interacting with the W and Z bosons, giving them mass. But the Higgs field did not interact with photons, and the photon remains massless. That asymmetry broke the unified electroweak field into 2 functionally different forces, a short-range weak force carried by heavy bosons like W and Z bosons, and a long-range electromagnetic force carried by and mediated by massless bosons, photons. Completely independently of what's happening with the W and Z bosons, the same newly switched-on Higgs field also started interacting with quarks and electrons via what's called a Yukawa coupling, where different particles couple the Higgs field with different strengths, which is why the top quark is so much heavier than the up quark, for instance. Again, that drag through the field effect is what gives quarks mass. In short, the weak force splitting off from the electromagnetic force and quarks gaining mass are two parallel consequences of the Higgs field switching on. A field is an invisible substance filling all of space. A particle is just a really weird way that field fluctuates. Lastly, an extra note, fields aren't sealed off from each other. They're wired together by a set of conversion rules. A photon field excitation can actually, in some cases, basically transform itself into a matched electron-positron pair, like when two photons crash into each other really hard. Anyways, in the ultra-hot early universe, there was an absurd amount of energy sloshing around, mostly in the form of photons colliding into each other. When two photons collide with enough energy, that energy can convert directly into a particle and antiparticle, like an electron and a positron. This happens constantly whenever there's enough energy density, and it happens in pairs because of some strict physical properties and laws, like charge, lepton number, baryon number, and so on. You can't actually just make one electron out of pure energy. You have to make an electron and a positron together. So, for a good chunk of the early universe, matter and antimatter were being created and destroyed in a constant, symmetric back and forth. Photons car crashing into each other produced particles and antiparticles, and almost every time, basically instantly, the particle and antiparticle pair crash back into each other and annihilate each other back into photons. Then those photons pair produce again. Matter and antimatter in this era existed in almost perfectly equal amounts, endlessly recycling into each other. If that symmetry had held forever, the story of the universe would end right there. Everything annihilates. You're left with a universe of pure light and nothing else. Another big mystery in science currently is what caused the particles to outnumber their antiparticle counterparts. For roughly every billion antimatter particles, there were the 1,000,001 matter particles. That tiny lopsidedness is the only reason anything exists at all. Once the universe cooled enough that pair production stopped happening, but annihilation kept going, all the matched pairs pretty much wiped each other out. And that 1 in a billion left over is everything you see today. Physicist Andrei Sarkov posited three conditions that any explanation of this asymmetry needs to satisfy. A process that can change the matter-antimatter balance at all, a violation of certain particle symmetries like charge and parity, and conditions far from equilibrium like a rapidly expanding cooling universe provides. But the actual mechanism that tipped the scales is still an open research question, with several competing theories and no consensus. So anyways, to summarize so far, the universe started expanding and cooling down from such a hot condensed state that the fundamental forces of nature literally were melted and fused into each other. As things cooled down and the energies of these fields started interacting in new ways, things started developing mass. During the aforementioned annihilation events of the early universe's generation of particle types via colliding photons, heavier particles needed way more energy, so they could only be made when the universe was still extremely hot, and they stopped being producible through those means once the universe cooled below a certain threshold, even though annihilation of any leftovers keep happening to this day. At different temperatures during this annihilation process, different particles got made. Working our way from hottest to coolest, and therefore chronologically in order of appearance, quark-antiquark pairs, up, down, strange, charm, bottom, top quarks, and their associated antiquarks, all got pair produced in the earliest, hottest instance alongside gluons. This era was before quarks got locked into protons and neutrons, and originally there was just the quark-gluon plasma soup so often referred to as the earliest matter as we recognize it in existence. W and Z boson pairs and other heavy force carriers came next. These are seriously heavy, so they only got made in the earliest, highest energy moments. Muons and tau particles, heavier cousins of the electrons and their antiparticles, same thing, needed lots of energy, so they dropped out of the pair production game earlier as things cooled. Neutrino-antineutrino pairs. Neutrinos barely interact with anything, but they were still being produced and were in thermal equilibrium with everything else in this era. Electron-positron pairs. These hang on the longest of all the matter pairs because the electron is by far the lightest charged particle in the standard model. Electron-positron annihilation was still happening, making up a good chunk of the photon bath, all the way up until about 1 whole second after the Big Bang, way later than quark or muon pair productions. Electron-positron pairs were the last matter-antimatter pair standing. Its final annihilation moment is actually a distinct named event in cosmology, sometimes called the EE annihilation epoch, separate from and after the quark-hadron level chaos. In short, quarks and heavy stuff first, then muons and taus, then finally electrons and positrons, and once even those stop being made, then the asymmetric matter left over pretty much becomes everything that we know. Those are what came about from the annihilation events of the early universe, which included, as mentioned, colliding photons, although similar collisions are going on in the early universe as well, all of which contributed to the creation and diversification of particles. The early universe was a thermal soup where practically everything was crashing into everything else. Quarks collided with quarks, gluons interacted with quarks, electrons scattered off photons, neutrinos exchanged W bosons with electrons, and so on, all constantly interconverting many different interaction channels simultaneously. Every particle type was being created and destroyed by multiple processes at once, fast enough that the whole system settled into a stable mix at whatever the temperature allowed. Let's now do a complete quick rundown of all the basics of atomic particles, starting again with some we've already covered, and adding the rest along the way to complete our picture of the standard particle of quarks and gluons as free individual entities existing as quark-gluon plasma came about during the first fraction of a second. Although at this time quarks were still massless, pre-Higgs field and all, just free-floating fluctuations of their respective fields, part of the primordial soup. W and Z bosons then appeared as soon as the electroweak field existed, but only became distinct from photons, another boson, at that time part of the electroweak field, once the Higgs field started fluctuating, less than a second after the Big Bang. The interaction with the Higgs field started to give the W and Z bosons mass. Before that moment, they weren't separable from photons at all, as they were part of the same unified electroweak field. The Higgs boson itself is worth noting separately from the Higgs field. The field starts fluctuating still less than a second after the Big Bang, but the Higgs boson, the actual particle associated with the fluctuations of the Higgs field, is a fleeting, ultra-short-lived excitation that would have been present as thermostatic in that same hot era. It's not something that populates the universe the way quarks or photons do, more of a transient byproduct. Quarks gained tiny amounts of mass, still way less than a second after the Big Bang. Quarks were still unconfined at this point, but this was the start of the quark-gluon plasma phase, which lasted up to about 1 millionth of a second. Again, quark-gluon plasma is the first stuff that we would recognize as traditional matter. Muons and taus, heavier cousins of the electrons, as well as their antiparticles, are pair-produced alongside everything else in this same ultra-hot window, dropping out of production as things cooled. Neutrinos and antineutrinos are also present in infernal equilibrium through this whole era. Because they interact so weakly with everything else, they decouple, that is, they stop interacting with other matter around 1 second in, slightly before electron-positron annihilation finishes, meaning there's technically a cosmic neutrino background out there too, just harder to detect than the cosmic microwave background. Protons and neutrons form again still less than a second in. The strong force combined free quarks out of the quark-gluon plasma as things cooled down via a process called confinement, locking them permanently into protons and neutrons with free quarks each. This is the end of free quarks existing everywhere in the normal universe. Electrons and positrons pair produced throughout, but distinctive as the last matter-antimatter pair made and annihilated. Since the electron is the lightest charged particle around, this continues until roughly 1 full second. From there, the matter-antimatter asymmetry finds matter the victor in the earliest squabble on record. Once photon energy drops below the threshold for further pair production across all particle types, only the 1 in a billion leftover of matter survived annihilation. And this is all within the first few seconds. Photons were technically present since the very start, as they are part of the electroweak field, but they only become free-roaming, unobstructed light around 380,000 years in, during the recombination era, when electrons finally bind to protons to form neutral hydrogen and the photon scattering fog clears. This is the light we detect today as a cosmic microwave background. So again, in brief, quark-gluon plasma are basically the earliest, then W and Z bosons became distinct from photons as the Higgs field started giving the W and Z bosons slight mass, and with the Higgs field fluctuating, quarks gained mass too. Muons and taus, which are basically heavy electrons, came about, then neutrinos, then protons and neutrons formed as quarks linked up, though didn't form atoms yet, because photons kept bouncing away electrons. Electrons and positrons were the last to come about from the early matter-antimatter annihilation process, then the matter-antimatter war reached its end, and matter won. Photons then scattered as free light, as we would recognize it 380,000 years later, during a process called recombination. I really find the Standard Model a real achievement and landmark for physical sciences. Kind of like the periodic table of elements for chemistry. It's right up there with Newton's laws of motion and the laws of thermodynamics. By the way, it's worth mentioning, side note, the two main types of fundamental particles are fermions, and the other, bosons. Fermions are matter as we would ordinarily recognize. Bosons are force-carrying particles. Fermions consist of quarks and leptons. Quarks, as mentioned, combine to form protons and neutrons. Leptons are stuff like electrons and their heavier variants, like muons and tau particles. Quarks are unstable and pretty much physically incapable of not combining in the current state of the universe. Leptons are relatively stable. Bosons, meanwhile, the force-carrying type of particles, consist of photons, W and Z bosons, and gluons. There is believed to exist, but not yet discovered, something called a gravitron, which would mediate gravity as a force, but it's unknown if it truly exists. Anyways, as I mentioned, various combinations of types of quarks binded by gluons are called hadrons. Now, most hadrons that we are acquainted with are baryons, which have free quark formations and include protons and neutrons as well as their counterpart, antiprotons and antineutrons. So, protons and neutrons are specifically baryons, which are a type of hadron, which is a type of fermion, which is a type of fundamental particle. There is another type of hadron, other than baryons, with a different number of quark formations. Baryons have free quarks, but mesons contain only two, a quark paired with an antiquark, though these are generally unstable and don't last long. In the same way photons are fluctuations from the electromagnetic field, quarks and gluons are fluctuations from their respective fields. They're just two fields whose fluctuations go on to combine into protons and neutrons, making them the primordial building blocks of atomic nuclei specifically. As far as we know, fields are not made of anything smaller. Quarks come in 6 types, up, down, strange, charm, bottom, top, each with its own correlated field. Gluons are the strong forces carrier particles, and they kind of act like energy between quarks, keeping them bound together. Protons and neutrons are quarks bound together by gluons. A proton is 2 up quarks and 1 down quark, held together by a constant exchange of gluons. A neutron is 1 up quark and 2 down quarks, same deal. The nucleus of an atom are protons and neutrons bound together by the strong force. Again, gluon is the carrying particle mediating the strong force, and the strong force does two different jobs at two different scales. Inside a proton, it directly binds quarks together via gluons. But between protons and neutrons and nucleus, it acts through something called the residual strong force, basically the leftover pull that leaks out from proton-neutron to proton-neutron, similar to how two neutral magnets can still weakly attract if you get them close enough. This residual force is what overcomes what is called electromagnetic repulsion, as protons all carry positive charge and want to push apart. But this residual strong force holds nuclei together. Get enough protons crammed in without enough neutrons to buffer that repulsion, and the nucleus becomes unstable, which causes radioactivity. But moving on. Atoms are a nucleus of these combined protons and neutrons, plus electrons, held together by the electromagnetic force, which is a very different force, though still a fundamental force-carrying field like the strong force. Though whereas the strong force is mediated by gluons, the weak force is mediated by W and Z bosons, the electromagnetic force is mediated by photons. Everything up through the creation of atomic nuclei is strong force territory. Atoms add electrons, which are themselves fundamental particles and excitations in the electron fields, not made of quarks at all, orbiting their respective nuclei, held in place by simple electromagnetic attraction. As nuclei are generally positively charged, and obviously electrons are negatively charged, this causes attraction. This is also the step that had to wait for recombination, 380,000 years in, since before that, the universe is too hot and photon-dense for electrons to stay bound. Photons, as I'm sure that you know, are light. All of which we see in the visible spectrum is because of photons bouncing around off everything, and the visible spectrum is just a small part of the electromagnetic spectrum, which includes everything from radio waves to microwaves. Infrared light is light that's slightly too slow for us to see. UV rays is light that's slightly too fast. Go even faster and you get X-rays, all the way up to gamma rays. It's all fluctuations of the electromagnetic field at different intensities, different speeds. It's all photons, that is to say, light at different speeds, different energy levels. Another thing on atomic nuclei. Most descriptions of atoms make electrons look like tiny planets circling a nucleus, but the actual quantum picture is a bit different. Electrons exist as probability clouds, sometimes called orbitals, around their nucleus. Not points tracing a path around a nucleus, no. There's no literal orbit, no defined trajectory. It's like a field in an area around each atom that kind of has a probability of having an electron in it at any time. Quarks and gluons build protons and neutrons. Protons and neutrons build nuclei. Nuclei attracts electrons because the negatively charged electrons are attracted to the positively charged nuclei. Then the whole gang creates atoms, and the different types of atoms just have different numbers of protons. 1 proton, that's a hydrogen atom. 2 protons, that's a helium atom. 69 protons, that's thulium, you fool. 420 protons? You can't do that. Once you get up to 118 protons, they get too big and heavy. I'm sorry. Neutrons vary independently, and that's what isotope means. 2 atoms can have the same proton count, meaning they are the same element, but have different neutron counts. They are 2 different isotopes of the same element. Carbon almost always has 6 neutrons, but carbon-14, used in radiocarbon dating, has 8. Same element, different mass, different stability. Some isotopes are stable forever, others are radioactive and decay over time. Nuclei existed as bare, unshielded positive charges surrounded by a chaotic soup of free electrons and photons for hundreds of thousands of years from early on, right after the Big Bang, before they were finally able to capture those electrons and become true, complete atoms. Everything heavier than hydrogen, helium, lithium, beryllium, or boron, every element except those had to wait for stars to form and create them in their cores. But that's a story for a different day. Right after the Big Bang, the average photon zipping around had more than enough energy to blast an electron right back off the nucleus the instant they bound, in a process called photoionization. So binding was happening constantly all over the universe the whole time, and electrons technically started forming during the process of nucleosynthesis right after the Big Bang. It just never stuck around. Whenever an electron would bind forming an atom, a photon would blast it off almost instantly. To clarify, Big Bang nucleosynthesis happened roughly 3 to 20 minutes after the Big Bang. This is when protons and neutrons fused to form the nuclei, not yet full atoms, of hydrogen, helium, and a tiny bit of lithium. The nuclei formed at 3 minutes, but the atoms, nuclei plus electrons, didn't form until 380,000 years later. Obviously, there is a lot we do not yet understand very well at all about the origin of the universe. Dark matter and dark energy, for instance, are big current mysteries in science that everyone knows about. A seemingly massive amount of stuff in the universe doesn't seem to interact with light, so we can't see it. It affects stuff gravitationally, though, so we can reason out that it's there. What exactly it is remains quite a mystery. We also aren't quite sure what the future of the universe holds, but there are plenty of guesses, most of which you are likely familiar with. Once atoms formed, the story of the universe beginning was over. What about its end? The Big Freeze, currently the leading candidate. The basic notion here is that the universe keeps expanding forever, and that expansion keeps accelerating. Stars burn out one by one and aren't replaced as star-forming gas runs dry. Eventually, even black holes evaporate via Hawking radiation over almost incomprehensible timescales. What's left is a fully stretched out and frozen universe at thermal equilibrium, with no temperature differences left anywhere, which means no usable energy, which means no possible process of any kind ever again. Not a bang, not a crunch, just a slow fade into permanent, eventless stillness. But this is no time for blind optimism. Another leading theory for what may happen eons out from now is the Big Crunch, the opposite of heat death. Instead of expansion continuing forever, gravity eventually causes expansion to reverse, and everything collapses back inwards. Galaxies, stars, atoms, all the way down to hot, dense point once again, essentially the Big Bang in reverse. This was a serious contender before dark energy was discovered, accelerating the expansion in the late 1990s. Current data makes it look unlikely, but it's not fully ruled out if dark energy's strength were to change over time. The Big Rip is a more violent variant of accelerating expansion. If dark energy's strength keeps increasing over time rather than staying constant, the expansion will eventually accelerate so hard that it starts overpowering smaller and smaller structures, first tearing galaxies apart, then solar systems, then planets, and then eventually ripping apart atoms themselves in the final fraction of a second. Everything ends not by fading out, but by being violently shredded by space itself, expanding faster than any force can hold matter together. I like this theory. The Big Bounce is a speculative alternative where the universe doesn't end in a big crunch so much as a recycling. Collapse triggers a rebound rather than a singularity, kicking off a brand new expansion, essentially a new Big Bang. Some versions propose this happens in an endless cycle, sometimes called cyclical cosmology. Vacuum decay, or false vacuum collapse, or, as I would call it, the Big Collapse, because all of these models need the word big in them, otherwise it's not official, proposes that, in layman's terms, the universe's vacuum or void of space might not actually be the true lowest energy state, just a false one sitting in a local dip. If some random quantum fluctuation anywhere in the universe ever tips the Higgs field into a true lower energy state, that change would propagate outward at the speed of light in a literal bubble, rewriting the fundamental constants and particle masses everywhere it touches, utterly destroying any structure, including atoms, in its path. I don't really buy this one, because it's too complicated for me to understand, so I objected on principle alone. The notion of proton decay is not a competing model so much so as an extra ingredient some versions of heat death include. If protons themselves are not perfectly stable, and some grand unified theories predict they are not, though it's never been observed, then over spans of time, vastly longer than the current age of the universe, even ordinary matter itself would eventually decay away into radiation, leaving nothing solid at all, not even the cold, dead husks of stars from a standard heat death scenario. So, the universe can either freeze, crunch up into a ball, get ripped apart, bounce back and start over, or possibly get glitched out of existence by an unlucky roll of quantum dice. You better hope you're right, Einstein. Here is my personal favorite model of what might happen in the long-term cosmic history, to close out. A certain variation on the Big Bounce, specifically conformal cyclic cosmology, as proposed by a guy named Roger Penrose. In the far future, all matter eventually converts into pure radiation. Stars die, black holes slowly evaporate via Hawking radiation into photons, and if certain particle physics theories are right, even protons themselves eventually decay. The end state Penrose proposes is a universe containing only massless particles, mostly photons, with no matter left at all. Massless particles, like photons, however, don't have a meaningful sense of size or distance or time built into their physics the way massive particles do. They travel at light speed regardless of scale, and their behavior is what's called conformally invariant, which means unaffected by stretching or shrinking space, only by angles and casual structure. So once the universe is only photons, the difference between unimaginably vast and cold and unimaginably tiny and hot stops being physically meaningful in the same way it would be for a universe full of matter. Because of that, Penrose proposes you can mathematically rescale the infinitely expanded, cold photon-only far future so that it becomes indistinguishable from an infinitely dense, hot Big Bang. Not because matter physically recompresses, but because a universe made purely of massless radiation doesn't have a fixed notion of scale for the rescaling to contradict. The end of one aeon becomes, through this conformal mapping, the beginning of the next. Instead of matter stretching until it becomes compressed again, Penrose's idea is that everything with mass eventually vanishes entirely, evaporates, decays, burns out, leaving a universe made purely of light. And the universe made purely of light, it turns out, doesn't have a fixed sense of big or small, so the impossibly vast, cold end of one universe can be mathematically identical to the impossibly tiny, hot beginning of the next. This is, for some reason, a weirdly funny notion to me. And needless to say, even though it's certainly not in the lead for likely candidate of cosmological models, it's still my favorite. Oh yeah, and to answer the question implied by the video title, hydrogen was just statistically speaking most likely the earliest atom. Hydrogen only needs one proton and one electron to bind. Helium, needing to hold two electrons around a nucleus with twice the charge, is slightly harder to bind. So, statistically, across the whole universe, hydrogen atoms would have been both the most numerous and among the first types to successfully form and hold. And the first atoms formed generally did not survive very long. There was billions of failed attempts happening constantly for, as mentioned, 380,000 years, until the recombination era. Photoionization destroyed the earliest atoms. So starting right around nucleosynthesis, minutes in, free hydrogen nuclei were constantly grabbing stray electrons, forming an atom for a fleeting instant, and almost instantly getting reionized by whatever one of the countless highly active at the time photons happened to hit it. This process of light warring with electrons happened across the universe non-stop for roughly, like I said, 380,000 years. The first earliest atom is not some single identifiable object, obviously. Atoms were technically forming basically the entire time, just never very long, until the photon bath finally cooled below a certain threshold and atoms could finally consistently form. Hydrogen atoms didn't fail to exist before recombination. They existed constantly for hundreds of millennia, just not very long, until it cooled enough. The first atom came along from a process that had been failing nonstop for hundreds of thousands of years, until it finally succeeded and stuck around. So yeah, that's why hydrogen is the most common element throughout the universe, and why helium is second place. By mass across the observable universe, it's roughly 75% hydrogen, 24% helium, and everything else, every other element on the periodic table combined, carbon, oxygen, iron, gold, all of it, makes up only about 1%. All this to say, yeah, the first atom was probably a hydrogen atom, likely in the first few minutes of the universe, but then likely got obliterated by photons. Around 380,000 years later, light itself chilled out and stopped bouncing off free electrons, and so atoms could finally form. Again, just statistically speaking, the first of which was probably hydrogen. And that is why we list hydrogen as number 1 on the periodic table of elements. Well, no, it's actually just because it has 1 proton, but whatever. I hereby propose to call the long-obliterated first hydrogen atom that formed in the early universe of the name Schmidt-Werben-Jaegerman hydrogen. Why? Because he was number 1.